Relationship between above-ground biomass and different vegetation indices of forests of Ri Bhoi District, Meghalaya, India. Abstract estimates of biomass in forests are generally based on allometric models relating either carbon or biomass to diameter at breast height, dBH. The aim of this study is to investigate the relationship between the above-ground biomass, AGB, and 4 different vegetation indices, viz. NDVI, Normalized Difference Vegetation Index, RDVI, Renormalized Difference Vegetation Index, MSAVI, Modified Soil Adjusted Vegetation Index, and OSAVI, Optimized Soil Adjusted Vegetation Index, of the subtropical broadleaf/subtropical evergreen and semi-evergreen forests of Nongkhyllem Wildlife Sanctuary, and Umsaw Reserve forests in Ri Bhoi district of Meghalaya in northeast India. The main objective of the study is to correlate the biomass obtained by allometric models through field investigations and the values of the vegetation indices obtained from Landsat 8 satellite imagery. Keywords: NDVI, RDVI, MSAVI, OSAVI, Nongkhyllem Wildlife Sanctuary, Umsaw Reserve Forest. Introduction. Biomass assessment is of great significance in the fields of forestry, ecology, economics, and environmental science. It plays a very important role in determining forest ecosystems' productivity through carbon, budgeting, and has complemented studies on the role that forests have in the global carbon cycle, Hall et al., 2006, Samajai et al., 2006, Zionese and Menkuksini, 2004. Biomass is a key parameter in the global carbon cycle as it can be used to quantify the carbon sequestration rate of ecosystems or carbon pools. This also helps in quantifying the fluxes of greenhouse gases absorbed and released from terrestrial pools to the atmosphere through changing patterns of land cover and land use. Cairns et al., 2003. Forest biomass is an indicator of carbon sequestration, and most researchers estimate carbon by assuming the carbon content of dry biomass to be a constant 50% by weight. Brown, 1986, Montagnini and Porras, 1998, as opposed to other researchers who have determined the total concentration of carbon from biomass to be 45% of its total weight. Whitaker and Likens, 1973. The total biomass is usually divided into 2 fractions, viz. above ground biomass, AGB, and below ground biomass, BGB, and most methods of biomass assessments are determined for the above ground biomass, AGB, of tree species, as this fraction generally represents a greater, more significant fraction of the total biomass in forest ecosystems, and this fraction is comparably less cumbersome to deal with during field measurements. IPCC, 2007. In any carbon-related study, determining the above-ground forest biomass is the juxtaposition for estimating the carbon sequestration potential as well as the carbon fluxes, and thus assists in ascertaining the contribution that terrestrial ecosystems such as tropical forests have on the global carbon cycle. Moreover, estimates of AGB can also be used to predict root biomass, which is generally estimated to be 20% of the above-ground forest biomass. Acknowledgement et al., 2002. Traditional biomass assessment methods based on field measurements are the most accurate methods. However, they are difficult to conduct over large areas and are costly, time-consuming, and labor-intensive. Atarki and Gloagan, 2014. Hence remote sensing data now plays a significant role in the estimation of biomass over large areas in tropical regions owing to the availability and accuracy of high-resolution images. ARS technology has been applied to biomass assessment in many studies. Maynard et al., 2007, Kanker et al., 2013, Wanasiri et al., 2013. Remote sensing can obtain forest information over large areas at a reasonable cost and with acceptable accuracy based on repetitive data collection with minimal effort. Liu, 2006. Many studies have shown that the method of determining relationships between field measurements and ARS data and then extrapolating these relationships over large areas is very useful. Foote, Boyd, and Cutler, 2003. To estimate the relationship between the field measurement of above-ground biomass and the remote sensing data, researchers have used linear regression models, Kobayashi et al., 2012, and multiple regressions with or without stepwise selection, Liu, 2006, Zheng et al., 2004, Koulibaly et al., 2008. There are innumerable methods employed for mapping and estimating the above-ground forest biomass for all the different land cover types, to name one, the judicious use of Landsat imagery, which are medium-resolution satellite images in estimating the attributes of forests through direct correlations or stepwise regression analyses with spectral bands, band ratios, or vegetation indices is a very practical method. Mainorn et al., 2011, Tarakunpasut et al., 2007. Generally, mapping of changes in land cover cannot be accurately determined through poor quality medium and low resolution satellite images. In this context, however, mapping of large areas by using high resolution images is expensive and users are required to possess a certain degree of technical skill for data interpretation. Thus, these issues pose a problem for developing countries who rely on open sources for data acquisition or who lack skilled personnel. Landsat series data is the most commonly used data for many geoprocessing applications, as the data can be obtained easily for free or at a fair price. Data sources such as forest inventory, field estimations, land use patterns, elevation, and remote sensing data can be combined and used for the prediction or various vegetation variables over large areas. Labrec, 2006. A hybrid supervised/unsupervised classification approach coupled with a geographical information systems (GIS) analysis has been employed to improve land use/cover mapping for Landsat data. Labrec, 2006, Oman and Gregory, 2002, Camusico and Ania, 2009. For the estimation of biomass, many studies show that satellite-based vegetation indices are most commonly employed. Schlurf et al., 2005, Footy et al., 2003, Hercom and Harrison, 1998. The present study seeks to correlate the relationship between above-ground biomass, AGB, and the different vegetation indices viz. NDVI, Normalized Difference Vegetation Index, RDVI, Renormalized Difference Vegetation Index, MSAVI, Modified Soil Adjusted Vegetation Index, and OSAVI, Optimized Soil Adjusted Vegetation Index. Vegetation has a high near-infrared reflectance due to the scattering of radiation by mesophyll cells of leaves and low red reflectance due to absorption by chlorophyll pigments. This is the fundamental concept in understanding vegetation indices, which are used in a variety of satellite-based vegetation index models for the evaluation of vegetation parameters such as leaf area index, biomass and other physiological activities. Verelst et al., 2008, Barrett and Guillot, 1991. Mathematical transformations of the original spectral reflectance used in the interpretation of biomass and land cover are known as vegetation indices. Patel et al., 2007, He et al., 2006, Raman et al., 2003. Vegetation indices, VIS, are used to remove the variations caused in spectral reflectance measurement while measuring biophysical properties caused due to soil background, sun view angles, and atmospheric conditions. Liu, 2006. There are studies that suggest the existence of a significant positive correlation between biomass and vegetation indices. Das and Singh, 2012, Heiskanen, 2006, Steininger, 2000, Boyd et al., 1999, Hercom and Harrison, 1998. Nonetheless, other studies have shown poor results. Schlurf et al., 2005, Footy et al., 2003. This field-based and remote sensing approach is of great significance in today's contemporary world, as the same can be used in the regulation of global carbon cycles under the REDD+ initiative. 2 Materials and methods. A. The study area. The area of study is located in Ri Bhoi district of the state of Meghalaya in northeast India. The district lies between 90°5 to 91°16 N latitude and 25°40 to 25°21 E longitude. It is bounded on the north by Kamrup district and on the east by Jaintia Hills and Karbi Anglong district of Assam and on the west by West Kasai Hills district. The recorded forest area of the state is about 17,146 square kilometers, which is 76.44% of its geographical area, FSI 2017. According to legal classification, reserve forests, protected forests, and unclassified forests constitute 11.71%, 0.13% and 88.16% of the total forests, respectively. The control of unclassified forests mostly rests with the autonomous district councils of Kasai Hills, Jaintia Hills, and Garo Hills. Ri Bhoi district is one of the components of the Meghalaya Plateau and has an estimated area of 2,448 square km, with a forest area of about 50% of the total area of the district. The physiographical features of the district are almost similar to that of East Kasai Hills district. Nongkhyllem Reserve Forest has a total area of 125.91 square km, of which 29 square km was designated as a wildlife sanctuary, whereas Umsaw Reserve Forest has an area of 0.44 square km. Meghalaya Forest and Environment Department, 2019. Ri Bhoi district experiences a varied range of climate, similar to the tropical climate of Assam at the adjoining areas near Assam and a temperate climate at the areas adjoining of the East Kasai Hills district. The areas bordering Assam experience hot, humid weather during summer seasons with an average temperature of 30 degrees Celsius, especially during the month of May to July, whereas the other areas adjoining Umiam and the East Kasai Hills district, the climate is relatively cold in winters and comparatively pleasant during the summer months. Thus, the temperature in the district ranges approximately between 2 degrees Celsius and 36 degrees Celsius. The district receives an average annual rainfall of 1,636.46 millimeters. The maximum rainfall is between the months of June and August. The forest type of the district is dominated by subtropical broadleaf, subtropical evergreen and semi-evergreen forests. Barrique et al., 2006. The main tree species are Tectona grandis, Shorea robusta, Castanosis species, and Schima wallachii. B. Methodology. I. Field assessment of above-ground biomass. In the present study, stratified random sampling was used for estimation of biomass, in which 12 plots were laid down in different homogeneous strata depending on the accessibility of the locations. The locations of the sampling sites were recorded by using a handheld GPS. The layout of all sampling plots were 31.6 x 31.6 m for vegetation, 5 x 5 m for shrubs and 1 x 1 m for herbs. The plots of shrubs and herbs were within the plot of tree quadrats. The field data collected was in the form of dBH of tree and tree height. Further, the biomass of trees was calculated by using different biomass equations which are related to its biophysical variables such as dBH, height, etc. Zionese et al., 2005. The biomass of each tree was calculated by computing the exponential of the different tree constants while adding and subtracting with the natural logarithm of the dBH of the individual trees as shown in the given table. The coefficient of determination, R2, of the different models, Table 1, was then obtained by correlating the generated value of above-ground biomass and the diameter at breast height, dBH. The model which depicted the highest value of R2 was used as the main model, and this model was then used for correlation of the biomass value with the different vegetation indices. Landsat 8 satellite imagery for the month of October 2016 was used in this study as the field assessment was done in this month. Layer stacking of the different bands was performed on ArcGIS 10.3 software for desktop. The different tiles, paths/rows, obtained were mosaicked and area of study was clipped using a shapefile of the area of study. The downloaded images are in universal transverse Mercator projection and it was reprojected to geographic WGS84 Zone 46N, spheroid, and datum Everest. A point shape file was generated for the sampling sites and overlaid on the corrected image for verification of the matching plots with respect to the ground. The Normalized Difference Vegetation Index of the areas of study was then obtained automatically from the composite image. As for the rest of the vegetation indices, raster calculation was performed using the raster calculator tool. The NDVI, RDVI, MSAVI, and OSAVI pixel values thus obtained were then used to carry out the correlation analysis between the VIS and AGB. 3 Vegetation Indices. The Normalized Difference Vegetation Index, ROUS ETAL, 1974, is the most commonly and widely used VIS for many applications in forestry-related studies. The NDVI is the ratio between maximum absorption of red wavelength due to chlorophyll pigments and maximum reflectance of infrared wavelength owing to leaf cellular structure. PIO-ETAL, 2007, Raman ETAL, 2003, Perulo ETAL, 1997. Image noise such as topographic variations, illumination differences, cloud shadows, and atmospheric attenuation, which are usually present in the separate bands, has been reduced in NDVI, HUT-ETAL, 2002, however, in dense and multi-layered canopy, NDVI shows some saturation. Tenkabale ETAL, 2000, Barrett and Guillot, 1991, Lillis-Eder, 1982. The NDVI is given by the equation, ROUS ETAL, 1974, in Table 2. Therefore substantial efforts were taken in improving and developing new vegetation indices like Renormalized Difference Vegetation Index, RDVI, Ruin and Brian, 1995. RDVI index is a modification of NDVI. The RDVI was developed to be a more advanced index, which would have the combined advantage of the Difference Vegetation Index, DVI equals NIR, Red, Jordan, 1969, and the NDVI. The soil reflectance is dependent on various factors, viz. soil moisture, organic matter, OM, soil types, and the presence of iron oxide, Hofer 1978. Dry soils exhibit higher reflectance in comparison to wet in the visible, mid-infrared, and near-infrared spectrum, Hofer and Johansson 1969. Soil-adjusted vegetation indices are used for reducing the effect of soil background reflectance. A modified soil-adjusted vegetation index, MSAVI, developed by Chi et.al., 1994, replaces the manual adjustment factor L, with a self-adjustment L. Another soil-adjusted vegetation index, OSAVI, developed by Rondos et.al., 1996 gives satisfactory results in reduction of soil noise for both low and high vegetation cover conditions. The different vegetation indices used in this study are given in Table 2. Table 2, Vegetation Indices. Vegetation. Equation. Reference. 3 Results and discussions. A. Above ground biomass. The biomass assessment was done using the different allometric models as shown in Table 1. The most promising allometric model was Chambers et.al., 2001, as it showed higher correlation between above ground biomass, AGB, and diameter at breast height, DBH, thus this model was more suited for obtaining the biomass values from the different plots. The biomass values contributed by shrubs and herbs was determined through destructive method. The data was then extrapolated to all the separate plots and added with the tree biomass values. Table 3 shows the respective allometric models used as well as the R2 value of each models after correlation between above ground biomass and diameter at breast height. B. Comparative correlation analysis between above ground biomass and vegetation indices. Comparative analysis of biomass and the different vegetation indices revealed the following results as shown in Table 4, which indicates that the vegetation indices have significant strong positive correlations with above ground biomass. The linear model with the highest significance was the NDVI model with an R2 value of 0.785, which is then followed by MSAVI with an R2 value of 0.773, then RDVI with an R2 value of 0.753, and lastly OSAVI with an R2 value of 0.7185. The results show that the correlation between NDVI/RDVI/MSAVI/OSAVI and above ground biomass is highly significant. Table 4 represents the regression analysis obtained from correlation between the field biomass and the corresponding pixel values generated from the rasters after employing the different methodologies. Table 2. The following figures 2, 3, 4, and 5, also show the computed maps along with their pixel values that have been generated for NDVI, RDVI, MSAVI, and OSAVI. For conclusion, the different vegetation indices showed positive correlation with the above-ground biomass of the subtropical broadleaf/subtropical evergreen forests of Ri Bhoi district. This study highlights the importance of vegetation indices in forestry-related studies, and this technique can be used for conservation-related applications and management of forest resources. The application of remote sensing techniques have provided a more rapid, more efficient, and timely estimates of biomass for the scientific management of forest resources as compared to the traditional approach of biomass assessment, which are cumbersome, labor-intensive and time-consuming. The study sites most likely had large amount of photosynthetically active vegetation, hence more reflectance, thus more vegetation implies a higher correlation with biomass, and this property however is reduced during the dry months due to the annual senescence of the deciduous trees and the low productivity during these months. Acknowledgement. The authors would like to acknowledge the Department of Forests and Environment, Government of Meghalaya, for granting the permissions required for field visits to Umsaw Reserve forests and Nongkhyllem Wildlife Sanctuary, as well as the Department of Science and Technology, Government of India, for sponsorship of the study.